All right, we are back in recording. So just real quick, I had sent a message out to you guys about that previous question you guys had asked me. So if you take a look at the graph of natural log, I just wanted to make sure we got this on video in case anybody's ever watching these someday. I was saying it backwards to answer whoever's question that was. Natural log of one is zero. So the graph of natural log goes up into that direction and then sinks that way. So when I was saying that natural log can't be zero, what I was referring to was the domain will never be zero. So when you look at the domain of this graph, it's just never going to cross over. But anything between 0 and 1, a negative number does exist there. Okay. All right. So um, let's do just a little bit of integration review, and then we will jump into our topic for this evening, which is going to be Euler's method. So integration review, I've got two problems on the screen that you guys can try. So see what you recognize, see what you can come up with. So I see two things being multiplied together here. And up above, this looks like something that could be factored and then kind of work accordingly from that. Okay. So take about, I don't know, 5, 6 minutes and try these two, and then we will put answers on the screen. Okay, go. Okay, so let's put some answers up here, see if we got the same thing. So here's what I got when I did these. So for the first one, this is your partial fractions. So when you go through, it's x plus 4 and x plus 2. And then solving off to the side, when you do your common denominators, you have to set x to -2 and -4 and go from there. The other one is your UDU VDB, so that's by parts and then works out accordingly. Any questions out there for either of those? Okay, so I'll give you two more and then we'll move on. So let's also have you guys try these two. So we're getting close to wrapping up what would be considered a unit in BC. So we've got all the different types of integration. Then we did the exponential growth and decay. Tonight, we're going to look at something called Euler's method. And then we have one little thing left, and that kind of wraps up what would be a unit in a normal year. So go ahead, take a couple minutes, do this. So hopefully it makes sense that this is long division. And then for the arc sine one, remember to do an inverse trig one with parts. You're going to make this 1 times arc sine is the trick to making that work. So that's going to be the two things multiplied together. Okay, go for it. Okay, into the last two. So if you're watching on the video, you might want to pause it so you can check out these answers, but see if those line up. So for the first one, we should have been doing long division. And in doing so, once you integrate the actual answer you get, we should have x to the third over 3, 6x squared over 2, which is just 3x squared, 21x. And then when you tackle the remainder, you can take the 85 out front, and that becomes natural log. And then down below for the arc sine, we need to start with 1 times arc sine, and then running through all of that should take you to the final answer down there. Okay, do you guys have any questions on the integration review? Okay, then let's have you recap a problem from the last class. I know we did some of these already, but let's just have you try it without looking at anything just to make sure you can do them. So this is one on exponential growth and decay. So it says a graduate student is studying a population of fruit flies. They work under the premise that the exponential population increases according to the law of exponential growth. If 100 flies were counted the second day and 300 were counted the fourth day, how many flies were in the original population? So remember, this is the one where we had to work backwards and there wasn't an initial condition given. So this was the one where we kind of made two equations, and since they were both equal to C, we could set them equal to each other. So like if this equals this and something else equals the same thing, then you can set them equal to each other. Okay, so take a few minutes and try that. And then after that, we will jump into our lesson, which is called Euler's method. Okay, so here is my work for that one. So again, if you're watching online, you might want to just pause this. But the trick is if they don't give you an initial condition that we need to come up with some equivalent equations here. So for this piece, we were able to figure out that C was equal to this. And then under the other condition, we were able to figure out that C was equal to that. So you could set them equal to each other, and then that gets you started on the problem. Okay. So if you guys have any questions on the additional integration methods or this exponential growth and decay stuff, you're more than welcome to ask me in school or whatever. Do you guys have any questions on any of that before we jump into tonight? Okay, go ahead, Brahma. I can't hear you. I don't know why. Yep, yep, got you now.
If you leave it as k is equal to natural log of 3 over 2, and then you plug into the equation with t is equal to 2, couldn't the 2's cancel out and then you just be left with e to the natural log of 3 instead of having the square root of 3?
Hold on, you just said a whole lot of things. Let me see what you just, where are you at here? Let me.
Sorry, if you so for you simplified k, so instead of having like at the last step where you simplified k, where it's half natural log of 3, which is equal to natural log of the square root of 3.
Mm-hmm.
If you leave it just as half natural log of 3, and then you plug it into the equation with t is equal to 2, don't the 1/2 and the 2, that t is equal to 2, cancel out? Like, does that work?
You're saying what you want to go up here where we plug in, and instead of you're leaving this half out front, you're not making it a square root. Is that what you're saying?
Yes.
Yeah, that should be equivalent.
Okay.
I think you'd have to check that in the calculator, but yeah, you didn't say anything that raised any red flags to me.
Okay. Great. Sorry, just wanted to check that.
Okay. All right, let me find for tonight. Okay, so this is called Euler's method. Okay, this is genuinely pretty easy. No one has too much trouble with this usually, so this is pretty straightforward. It is important though. You're going to see this a couple times on the BC exam, so that's good news because this isn't too hard once you get your head wrapped around it. Euler's method is basically a different method for differential equations. So like whenever we were starting to learn differential equations, so you'll see as we go through this problem, when you do the differential equation stuff, you're basically taking the derivative and trying to figure out what the original equation was. This method is an estimation for the same thing. So if you need to remind yourself what it is, it's basically an estimation method of differential equations. And then you'll see when we compare those here in a second, how those work out. Okay, anyways, when you hear Euler's method, or you see that you're going to do one, the first thing we do is we're going to make this table. And the table is always x, y, dy, dx, tangent line is how I list the different columns on my table. X, y, dy, dx, tangent line. And with that information, we want to keep in mind that we're going to be using the previous line for each new line of information. And we're going to be looking for a step size in the directions. Okay. Okay, so usually the first time you do one of these, it's a little messy. And then like right around the second one, you're going to kind of start to get it. Okay, so our example says, given that dy dx is equal to x plus 2 and the initial condition y of 0 is equal to 3, we're trying to approximate y of 1 using Euler's method with 2 equal steps. This is what we said is the step size. Okay. All right, so let's see. what that means. So we are going to try to find a pen here. This marker is going to go through the paper. This is a two-sided. Let's make our table. So we've got X, Y, dy, dx, tangent line. All right, so we are starting at the X value of 0, and we're trying to figure out what happens when we plug in 1. And we are going to do 2 steps of equal size. So that means that if we're going to go from 0 to 1 using 2 steps, there's a step, there's a step. If we're going to make 2 jumps, 2 steps, equal step size would be 0.5 for each step. Okay, so we're going to go back to the beginning. And what you do is you're looking for the completed point. So we know that 0 was paired up with 3. And then for dy dx, we want to know what is dy dx at that point. So we're going to plug in 0, 3 to dy dx. And when you do that, the only plug-in spot is x, which is 0. So that's going to give us dy dx is 2. And now we want to write the equation of the tangent line using that information. So we can just do point slope form. So that is y minus 3 is equal to 2 times x minus 0. And that's with the 0.03. We got the slope. Here's our tangent line. So now we head to the next line of the table. And this is kind of where up above I said, here's these directions. Use the previous tangent line to plug into. So when we're now trying to figure out 1/2, hang on, question in chat. How did I get 2 for dy dx? Okay, so we have dy dx up here. And dy dx is x plus 2. So you're going to plug in this point to dy dx, whatever it is. Now, there was no y to plug in. So the only thing I was able to plug in was 0 for x. And that gives you the 2 for dy dx. Okay, so now we're going to take this half and we are going to plug it in to the previous tangent line. So what you're basically doing is using a series of tangent lines to come up with an estimation. So if I plug in 1/2 to this, this is going to be, well, I'm just doing my work off to the side. This is like scratch work over here. So y minus 3 is equal to 2 times 1/2 minus 0. And we're going to solve this out. So y minus 3 is equal to 1, y equals 4. So now I've got my 4. Okay. And now we're going to take our point, and now you just keep repeating this process. We're heading up to dy dx, and I'm going to plug in 1/2. So 1/2 plus 2 is 2.5, and I like fractions personally, so I'm going to call that 5/2. And now I want another tangent line. So this tangent line is y minus 4 is equal to 5/2 times x minus 1/2. Okay. And now we've got 2 lines completed. Now I'm going to take my 1, I'm going to keep going, but don't forget, remember what we're looking for. We are looking for y of 1, right? So in other words, once I get this value right here, this answer that we're coming up with right here in a second, that's the answer we're looking for. So we're just going to do this one more time. And when I plug in 1, where do I plug into? The previous tangent line. So this is y minus 4 is equal to 5/2 times 1 minus 1/2. So this is y minus 4 is equal to 5/2 times 1/2. Y minus 4 is equal to 5/4. Okay, if I add 4 to that, that's really going to be what, 16/4 when we do a common denominator? So that is going to be 21 over 4. And if you're doing decimals, 21 over 4, how many times does 4 go into that? 5 times with 1 left over. So you could say that that's also equal to 5.25. So depending on if the question was written in decimal or fraction form, those two would be equivalent. Okay, so that's essentially Euler's method. Now we'll explore it using a few different types of problems and see what other questions they ask. But before we go any further, do you guys have any questions on procedure? How'd you do this? Where'd you do that? Anything like that? Okay, question in chat. How did I get the second dy dx? Same way we got the first one, just with a different ordered pair. So we plug in a half comma 4 to dy dx. So the only plug-in spot is x. So if I put a half into that, that's going to be a half plus 2, and that's 2.5, also known as 5 over 2. Anybody else with any questions on that? Okay, then the next piece of this is kind of like a free response, actually. Solve the differential equation. We're going back to the one we started with. So now this is using actual free differential equation method. So if we are going to take this and we are going to actually solve it out, what's the first step for solving a differential equation? We want to split the variables up. So this would be dy is equal to x plus 2 dx. Now, since there's nothing over here with the dy, we're going to call it 1 dy. Okay. And now we want to integrate both sides. And if I integrate the number 1, I should come up with y. And if I integrate the other side, that should be x squared over 2 plus 2x plus c. Okay, now I want to solve for c. So I have this point up here to help me do that. If I plug in 0, I should get 3. That's into the original y equation. If I plug in 0, I should get 3, which means c has to be equal to 3. Because if I plug in 0 and the result's 3, these both disappear. C would have to be 3. So we're going to say that knowing that c is equal to 3, what does that make our equation? Y is equal to x squared over 2 plus 2x plus 3. Okay, and we are looking for the same thing we did up above, find y of 1. Okay, so if we put 1 into this equation, that's going to be a half plus 2 plus 3. So that is 5.5. So using the differential equation method, we can see that the actual answer is 5.5. The Euler's method, which was an approximation, is 5.25. And then the question asks down below, what is the error in using Euler's method? So if you're looking for the error between the two, all we're going to do is just take the actual answer minus the one from Euler's, and that should give us 0.25, which is how far we were off between those two answers. Okay. All right, what do you think? Any questions, comments, thoughts? I will show you 2 more examples tonight, but that is essentially Euler's method.
Where did the error originate? Like, why is there an error?
Well, so the thing is like when you're doing part B, this is exact, right? We are taking the derivative. We know this point. We're using integration. This is the exact original equation. And when you plug it in, this is the exact answer. This would be like if I just told you the derivative, if I tell you the derivative is x squared, we can say pretty quickly that if you integrate that, that would make the original equation x to the 3rd over 3. And then if I want to plug something into that, we're all in agreement. Yep, that's the answer. Whereas up here, what you're doing, it's kind of hard to graph this out, but if you like Google Euler's method and kind of look for a visual, you're essentially using repeated tangent lines. So like we're using repeated tangent lines and plugging into them to approximate where we end up at. But when you use this, this isn't an exact answer. These tangent lines are approximations. So it's going to be off by just a hair. And then if you want to find how much it was off by, basically you do part B and then subtract the two answers. All right, let's look at the following. Suppose a can, yes.
Where did why did we set it equal to 1 dy?
So yeah, that's one of the things where we need to get into this more in calculus AB. So like in normal circumstances, you would have already had all the differential equation stuff prior to tackling this. When you're doing differential equations, which good news, that's our lesson that we are starting next in AB. So you'll get more background on this. The goal is we want to split the variables to each side. So X's are going to go on the right, Y's are going to go on the left. And in this case, we didn't have any Y's. So if you just have nothing dy, it's the same thing as integrating the number 1 because there's always something there. That's like saying if there's no coefficient in front of a number, it's just 1. So if you have a blank set in front of dy, it just becomes the number 1. And then on the other side, when you integrate that, you go with that. But the goal of differential equations is split the variables. X's are on the right, Y's are on the left. Any other questions? Okay, let's check out example 2. So suppose a continuous function f and its derivative f prime have the values listed in the table below. Use Euler's method with 2 steps of size. Delta x just means that's going to be our step size to approximate f of 3. So the first thing that I would be doing is I heard Euler's method. I would be making a table. And my table should go X, Y, dy dx, tan line. And it says that we're looking for f of 3. So 3 is the end game, whatever that answer is. And since we're using 2 steps with a step size of 0.5, I can work backwards and say that's where I start at is going to be at 2. Okay, so see if you can work through this. Now you have a table of values up above. So like if I want the corresponding value for 2, looks like the corresponding y value for 2 is going to be 5. And then you would go from there. Okay, so see if you can work through it, and we'll talk in about 2-3 minutes. All right, so let's check this out here. Anybody have a final answer they want to share? See if they got it right. Any brave people out there?
10.
What'd you get?
10.
We are not in agreement, but I appreciate the
I got
volunteering.
6.7.
I got
Uh,
5.5.
okay, what'd you get, Rayanne?
5.5.
Oh, I got 5.5 too.
Yeah, I got 5.5 is what I got. So let's check it out. So, I said, here's 2 comma 5, and then let's see what happens. We need to look up dy dx. So dy dx for 2 is going to give us 0.4. So then that gives you your first tangent line. And then the next thing we need to do is plug 2.5 into our tangent line, which that is this math right there. So if I plug in 2.5 to my tangent line, that wraps its way around 5.2. And then I need dy dx at 2.5, and this table tells me that's 0.6. And then same deal, I could have filled in my tangent line up here, I just didn't. So your tangent line is y minus 5.2 is equal to 0.6 x minus 2.5. And then plugging 3 into your previous tangent line, which is what I did there, should yield a result of 5.5. Questions, comments, thoughts? All right, let's have you guys try one more. This will be our last one of the night. So let's take a look at the following. Now, take a peek here. Now your dy dx has both variables in it. We are going to use 2 equal steps, and we're going to try to approximate negative 0.6. So that should make your step size negative 0.3. So go slowly, see what you come up with, and we'll talk in a couple minutes. All right, anybody out there got an answer?
0.25.
Anybody agree? That's alarming. Nobody else out there agrees?
I agree.
All right, Jake agrees. I agree too. I got 0.25. Good, very good. So check it out. And the thing with this is, so it's very easy to make a math calculation error with this. The math is all over the place. So important thing is you understand the procedure. If your procedure is right, and you just made a math typo, do your best, try to go through and obviously try to avoid that. But important thing is that the procedure of this is making sense. So starting with 0 to -0.3 to -0.6, you can check your work from there. Do we have any questions? All right, guys, that wraps up Euler's method. The only thing we have left is called logistical functions or logistical growth. There's not a whole lot to that. It'll be a pretty simple lesson, I think. So we will tackle that tomorrow night. And then I think that puts the schedule I had posted off by a day. So we'll tackle that tomorrow. And then after that, I will send you guys a study guide basically for this unit in BC, because after tomorrow night, that's what you would have been taking a test on in BC. So I will have you guys complete that study guide as homework for Thursday night's session. And then Thursday night's session, we will just go over that whole study guide and record it and take questions and answers and stuff like that. So if you don't have any questions, I will see you guys tomorrow night. Enjoy your day off tomorrow from school.
Thank you. Bye.
You got it.
Thank you.
Thank you.
Thanks. Have a good one.
Have a good one.
Mr. Baker,
Yes.
um,
Hello. I can't hear you, Caleb.